Section 8.6 has us solving equations involving radicals. So in this section, we're going to use the squaring property of equality, check possible solutions, solve equations containing a square root, solve radical equations by squaring a binomial, and solve equations containing two square roots. First, we're going to use the squaring property of equality. Basically, what that tells me is, if I take something that's under a root and I square it, those are inverse operations. So the square root and the squared undo each other, and basically what's under the root symbol originally just comes outside of the root symbol. So basically, if we have the root of something and we square, that's the way to undo a root symbol and get something out of a radical to now be combined with other things that were already outside of a radical. So the squaring property of equality says that if a equals b, then a squared equals b squared. In other words, if we previously had equality in an equation, squaring both sides maintains that equality. It's a tool we can use in order to solve for a variable in an equation. So if, for instance, we knew that the root of x equaled 6, we could square both sides. Squaring the side with the x would get rid of that root symbol and just give me x. Squaring the 6 would give me 6 times 6 equals 36. So the answer to the root of x equals 6 would be x equals 36. Remember, we're only considering the positive form here. We can go back and check and see that if we put 36 in, it does equal 6 because the root of 36 is 6. So we see that 36 is the correct solution and is the solution set here. We do want to check solutions just to make sure that what we get as an answer does work if we plug it back in. So if we, for instance, considered the equation x equals 2, the only solution to this equation is 2. If we squared both sides to get x squared equals 4, now when we take a square root, we could get positive and negative 2. Problem being that negative 2 shouldn't have been a solution. So the solution negative 2 satisfies x squared equals 4, but it doesn't satisfy the original equation x equals 2. Squaring both sides of an equation can produce solutions that don't satisfy the original one. We call that an extraneous solution, and we really need to check for that as we go and make sure whatever we get as our final answer does work if we plug it back into the problem. When we want to solve an equation with a square root, we follow these steps. Basically, to begin, we want to make sure that the root is isolated on one side of the equation and everything else is taken to the other side. So isolate a radical term on one side of the equation. Once I have that root isolated by itself, if I square both sides, it'll undo the root. At that point, I either will have x squared terms left in the equation, in which case I want to take everything to the same side and factor, or I'll just have the single power of x, in which case I want to solve it by taking variables to one side, numbers to the other, and using the regular methods that we have in this course to solve a single variable equation. Once we get a solution, we want to check the possible solutions in the original equation. We want to make sure that we don't have any extraneous solutions. So let's say we start with the root of x plus 2 equals 3. In this case, the root is isolated on the left-hand side already. There's nothing with it. It's just everything under the root. And on the right-hand side is everything else. If we then square both sides, what's going to happen on the left is this x squaring is going to undo this square root and just leave me with x plus 2. On the right, 3 squared is 3 times itself, or 9. So I'm left with x plus 2 equals 9. I can subtract 2 from each side and get the answer of x equals 7. I can then plug this back in, see if it's true. If I put that 7 in where I see an x in the original equation, 7 plus 2 is 9. The root of 9 is 3. So we can see that substituting in does give us a true statement, meaning this is not an extraneous solution. 7 is the correct solution to this equation. Here's some example problems for me to try on the whiteboard. Our goal in these types of problems is to isolate the root on one side of the equation, then square both sides, which will get rid of the root. In A, we already have the root isolated. It sets up as the root of x plus 1 equals 2. So if I square the left-hand side, square the right-hand side. On the left, squaring and a square root undo each other. So basically, I'm just left with what's outside the square root, x plus 1. Used to be under the root. These two undo each other and just leave me with what was underneath the root. On the right-hand side, 2 to the power of 2, or 2 squared, is 2 times 2, which is 4. I then have an equation that's easy enough to solve by subtracting 1 from each side. That gives me the correct final answer of x equals 3. B is the same general idea, I just have to make one move to make it similar. Basically, this plus 4 is with the root right now. If I want to isolate the root, I want the root alone, so to get rid of a plus 4, I subtract 4 from each side. That leaves me on the left still with the root of x minus 5. On the right, 7 minus 4 is 3. Since I have the root isolated, I can square each side of the equation. On the left-hand side, the squared and the root undo each other, and just leave me with x minus 5. On the right-hand side, 3 squared is 3 times 3, or 9. If I now add 5 to each side, I get the correct final answer of x equals 14. In part C, I'm going to start again by trying to isolate the root. Right now, 8's being added to the thing under the root, so I'm going to subtract 8 from each side. When I do that, I get negative 5 on the right, and I get the square root of x minus 2 on the left. Right here is where I should know something went wrong. We're only considering the positive form of the root, so if I get root of x minus 2 equals a negative number, I have to say no solution. I cannot solve where I get a negative number out of the root. For that reason, I would stop here and write no solution. If I didn't recognize that this was a negative being set equal to a root, I could have squared both sides. I'd get x minus 2 equals 25, and then it would look like x equals 27. But if I put 27 in here, 27 minus 2 is 25, and the root 25 would really be positive 5, not negative 5, the way that we've been working with it. Solving radical equations by squaring a binomial is going to create a little more work for us because it's likely this is going to end in a quadratic equation that we need to factor to solve. Many of these problems are going to have 2 answers instead of 1. So let's say we have a plus 2 equals the root of a squared plus 3a plus 3. In this case, we have isolated the root on one side of the equation, but on the other side we have both a variable and a number. Have to remember that when we square both sides, squaring the a plus 2 doesn't give me a squared plus 4. Very common mistake that students make, just trying to distribute that square. You don't want to do that. You want to see the a plus 2 quantity squared as a plus 2 times a plus 2. If you see it that way, a plus 2 times a plus 2 gives you a squared plus 4a plus 4, because you also have 2 times a and a times 2 being added together to create this middle term. In the end, I have a squared plus 4a plus 4 from squaring this, and I have what was under the square root, a squared plus 3a plus 3, that all comes out on the right-hand side. Since I see a squared in the problem, my first thought, I should say, is probably to bring everything to the same side so that I can solve by factoring. But in this case, if I try and bring the a squareds to the same side, subtracting a squared and subtracting a squared is going to make them drop out of the problem. So really, the single power of a is what's going to remain, which means I want a's on one side, numbers on the other, to then solve for what a should equal. So as you can see, we're going to first subtract the a squareds from both sides to get them out of the problem. Now that we just have the single power of a in the problem, I'm going to take letters to the left, numbers to the right. So if I subtract 3a from both sides, minus 3a here means I'm just left with 3, minus 3a here, 4a minus 3a leaves me with a. So I now have a plus 4 equals 3. If I subtract the 4, that's going to leave me with a equals negative 1. A equals negative 1 is my final answer to this problem. I would just want to go back and check to make sure that it works in the original equation. So if I plug in a negative 1 plus 2 equals the root of negative 1 squared plus 3 times negative 1 plus 3. What that gives me is 1 equals the root of 1, which is true. So this is the correct answer to that equation. You'll see that in some of the problems that we do as examples, there'll be more than one answer. So let me try these example problems on the whiteboard. In these examples, we're likely to get more than one answer for x. What's going to end up happening is we get an equation which we'll have to factor. Once we have the factored form, we can find what makes the values 0. So where I want to begin is by making sure that I have everything on one side of the equation and only the root isolated by itself on the other side of the equation. Currently I see one root in the problem with 1 being added to it, so I'm going to subtract 1 from each side. That leaves me on the left with x minus 1, on the right with the root of 2x minus 2. If I now square both sides, on the right hand side, it's just going to come out of the square root and become 2x minus 2. On the left hand side, I need to remember that when I square x minus 1, it really means I'm doing x minus 1 times itself. The very important thing is this middle term that's formed. So I have x times x equals x squared. X times negative 1 equals negative x. Negative 1 times x equals another negative x. And negative 1 times negative 1 equals positive 1. These negative x's are the important part that a lot of students neglect when they go to square x minus 1 squared. A lot of students say, well, I can just distribute that square, make it x squared plus 1. Absolutely not true. You need to multiply it out and make sure you're considering that middle term that's created. If I combine like terms here, I'm left with x squared minus 2x plus 1 equals 2x minus 2. I can now subtract 2x and add 2. Subtract 2x and add 2. Over here, this will go away and this will go away and just leave me with 0. Over here, I'm left with x squared minus 4x plus 3. If I go to factor x squared minus 4x plus 3, I put in my two parentheses, x and x. First sign negative, second sign is telling me same as negative is another negative. I'm looking for two things that multiply to 3 and add to 4. That'd be 3 and 1. What would make this factor 0 is a 3. What would make this factor 0 is a 1. So the x values that make this statement true are x equals 1, 3. For part B, I already have the root isolated. On this side I have x minus 1. I need to square it and square the right side. X minus 1 squared is exactly what we did above, so we get the same thing, which is x squared minus 2x plus 1. When I square a square root, it gets rid of it, so I'm left on the right with x squared minus 4x plus 9. If I decide to move all the x's to the left and all the things that are not x, the numbers to the right, in this case, my minus x squared makes the x squareds go away on each side of the equation and leaves me with no x squared terms. If I add 4x to each side, then the right side, the x terms will go to 0. I can subtract 1 here, subtract 1 here, so that my x squareds go away, my 4x's go away on this side, and my 1 goes away on this side. Negative 2x and positive 4x leaves me with positive 2x. Positive 9 and negative 1 leaves me with positive 8. I can then divide both sides by 2 to get my final answer, which is x equals 4. For part C, I need to begin by moving this x to the other side. So I'm going to do plus x here, plus x here. That leaves me with the root of 7 plus 6x equals x plus 2. I now have the root isolated, so I can square both sides. That'll get rid of the root in the problem. So the left-hand side becomes 7 plus 6x. The right-hand side is x plus 2 squared, or x plus 2 times x plus 2. When I square that out, so on the left I still have 6x plus 7. I'm just rearranging it so that the x terms come first. On the right, x times x gives me x squared. X times 2 gives me 2x. 2 times x gives me another 2x. 2x plus 2x gives me 4x. And then positive 2 times positive 2 gives me positive 4. I'm going to subtract 6x, subtract 7, subtract 6x, subtract 7. Over here, that leaves me with 0 equals x squared. 4x minus 6x is negative 2x. 4 minus 7 is negative 3. If I now factor this, I'm going to make my two parentheses, x and x. First term is a negative. Second term, different from a negative, is a positive. I'm looking for two numbers that multiply to 3 and subtract to 2. Two numbers that multiply to 3 have to be 3 and 1, and they do subtract to 2. So to make this part 0, I'd have to put in x equals 3. To make this part 0, I'd have to put in x equals negative 1. That's why my final answers are x equals negative 1 and 3. When we solve equations containing two square roots, we want to get one square root isolated on one side of the equation and the other on the other side. So in this case, we have a root on the left, we have a root on the right. This 3 outside isn't ideal, but at least it's being multiplied, not added or subtracted. If it was added or subtracted, it would create new roots in middle terms, and I'd have to go another level deep in order to solve it. In this case, I just have to be aware that when I square this side, it's going to get rid of this root, but that 3 is also going to be squared to turn that 3 into a 9. So I start by putting parentheses around both sides and squaring everything. On the left-hand side, this squared just gets rid of this root. On the right-hand side, this squared gets rid of this root, but it also squares the 3 that was outside of the root. So I'm left with what was underneath on the left, which is just x plus 12. And on the right, what was underneath x plus 4 comes out, and the 3 times itself gives me a 9 outside. I now want to distribute on the right-hand side 9 times x and 9 times a positive 4. That's going to give me x plus 12 equals 9x plus 36. I'm going to move this x over here to get 8x. I'm going to move this 36 over here to get 12 minus 36 equals negative 24. They did it the other way, so negative 9x here, negative 9x and a 1x combine to give me negative 8x. Subtract 12 here gives me a 24. Either way would get me to the same answer. In this case, they're going to divide by negative 8. In my case, I would divide by positive 8, but you would have seen things on the other side, and the 24 would have been negative. In either case, the final answer you should get should be negative 3. If x equals negative 3, I want to plug that back in to make sure it's not an extraneous solution. So when I put in a negative 3 over here, negative 3 plus 12 gives me a positive 9. The root of 9 is 3. When I plug in a negative 3 here, negative 3 plus 4 gives me 1. The root of 1 is 1 times 3 is 3. So you can see that by plugging in that negative 3, we get 3 equals 3, which is a true statement. So it's an actual solution, not an extraneous solution. I'm going to finish by showing these example problems on the whiteboard. When there's two roots in the problem, we want to get one to either side and then square both sides. So in example A, we already have one root on either side. We can jump right to squaring. I'm going to square this side, square this side. In both cases, the squaring undoes the square root. So what was under the root just comes out, x minus 3. What was under the root just comes out, 2x minus 11. If I now add 11 to each side, subtract x from each side, these 11's go away, these x's go away. On this side, I have a negative 3 and a positive 11. That combines to make 8. On this side, I have a positive 2x and a negative 1x. That gives me 1x. So my final answer is x equals 8. You can see that if we plug that back in, 8 minus 3 would give me 5, so I'd get the root of 5 on this side. 8 times 2 is 16, minus 11 is also 5, so I'd also get the root of 5 on this side. In part B, we don't have the two roots on either side of each other, so I need to move this root. If I do plus the root of x plus 8, then this root 2x stays on the left. Where I used to have 0, I now add the root of x plus 8. So it becomes root 2x equals root x plus 8. I can now square both sides because I have the root isolated on each side. Here, the root goes away and just leaves me with 2x. Here, the root goes away and just leaves me with x plus 8. If I now subtract x from each side, 2x minus x equals x. These go away and just leave me with x equals 8. For the final problem, again, I have the roots on either side, so I can just square both sides. On this side, I get x squared plus 12. On this side, I get 8x. I'm then going to subtract 8x from each side. That leaves me on the left with x squared minus 8x plus 12, and on the right with 0. I can now factor to find my possible answers. If I make my two parentheses, x and x, bring down the negative sign. Positive means same as a negative is another negative. I'm looking for two things that multiply to 12 and add to 8. That would be 6 and 2. 6 times 2 is 12. 6 plus 2 is 8. So I put the larger one here, the smaller one here. I'm now looking for what would make either of these factors 0. If I put in a 6 here, 6 minus 6 would give me 0. If I put in a 2 here, 2 minus 2 would give me 0. So that's how I get my final answers of x equals 2, 6.